Hello, in this video we're going to be dealing with a cup that is spinning on a turntable at an angular frequency, and we're going to try to find what that maximum angular frequency needs to be or is before the water spills out of the cup. So we have a cup with an initial fluid height. We're also given the height of the entire cup, so we'll define that as capital H, and the initial height of the fluid as H naught. And we're also given the radius of the cup. And so we're told that it is spinning at some angular frequency. So what it's going to look like while it's spinning is it's going to have some kind of parabola, that's a depression in the fluid height. And right here, we'll define the radius as equal to 0. And we're also told that the pressure is equal to 0 within this interface. And so, if we are at some point and we are given the height at some point within the spinning cup, we want to know what the angular frequency is. And so we're going to use the definition of pressure, because we're going to be looking at what the pressure in the horizontal direction and in the vertical direction is. So first, in the horizontal direction, we're going to use the definition of pressure force, which is that it is pressure 1 plus the density times the angular frequency squared divided by 2 times the quantity of the radius squared minus the radius 1, so the initial radius squared. And so we are told both that the initial radius, we're setting it equal to 0, so that will zero out this term. And we're also told that the pressure is atmospheric in this interface, so that is also zeroed out, which leaves us with the pressure in the horizontal is equal to the density times the angular frequency squared divided by 2 times the radius, which we're given the radius as a big R squared. And then the pressure in the vertical direction is going to be the density times the gravitational acceleration times the height. And so now the horizontal and vertical pressure equal to one another because they're the same. So we have the density times the gravitational acceleration times the height is equal to the density times the angular frequency squared divided by 2 times the radius squared, and we can cancel out terms. So we can cancel out the density, and then we can solve for the height, which is what we're looking for, is the height of the liquid as it's spinning. And so that's going to give us the height is equal to the angular frequency squared times the radius squared divided by the gravitational acceleration times 2. And so, in theory, what you could do is set this equal to the height of the cup minus the initial height, and set that equal to the height that we just derived. But the reason that we can't do this is because the low point of the fluid is constantly changing. So what we actually have to do instead is find the volume of the depression in the fluid. So as you can see, there's initial fluid height here, and so from the initial fluid height down to the low point of the fluid, we have a depression. And so the liquid that is in this area here actually spins out and becomes the liquid that is in this area here. And so what is the volume of that depression? So the volume of the depression is the surface area times the height of the depression, so that's going to be pi times the radius squared times the depression height. And then, so now if we were to take a look at this cup from a bird's eye view, we would have a circle. And what we can actually do is take out little slivers of the water that's inside the cup that's spinning up, and we can find what the volume of those little slivers are and integrate them to figure out what the volume is at certain points. And so that would give us the integral, and so we have 2 pi r, which is the radius from here to whichever point we're going to, times the height at which we're trying to figure out. And then since we're taking just little sections of the radius, it will be, so this will be dr, is this little section here, and then we have the radius of the entire circle. And multiply that. And then our limits of integration is going to be from the center to the outer circle. And so now what we can do is set the volume of this depression to what's the volume of the slivers that we cut out from. So basically we cut out little slivers here of the cylinder, and so that's going to give us pi r squared times the depression equals the integral from 0 to r times 2 pi r times the height times the differential radius. And we are going to take out the constants in the integral. So that's going to be taking out the 2 pi and keeping the radiuses in this integral. So the integral from 0 to the radius times 2 pi times the radius times the height times the differential, or excuse me, we took the 2 pi out, so it's going to be the radius times the height times the differential radius, and then we can plug in our equation for the height here. So on the left it's going to give us pi times the radius squared times the depression times 2 pi times the integral from 0 to the radius times the radius times the height, which is the angular frequency squared times the radius squared, divided by 2 times the gravitational acceleration times the differential radius. We can take the constants outside the integral, so that's going to give us pi times the radius squared times the depression equals 2 pi times the angular frequency squared divided by 2 times the gravitational acceleration times the integral. This r is going to multiply with that r squared, which is going to give us the radius cubed, times the differential radius from 0 to the radius. Canceling out like terms, we can cancel out the pi, the 2's, and so that's going to leave us with the radius squared times the depression equals the angular frequency squared divided by the gravitational acceleration times the integral of 0 to the radius of the radius cubed times the differential radius. Solving that integral, it's going to give us the radius squared times the depression equals the angular frequency squared divided by the gravitational acceleration times the radius to the 4th divided by 4, evaluated from 0 to the radius. So with that evaluation, it's going to give us the radius squared times the depression equals the angular frequency squared divided by the gravitational acceleration times the radius to the 4th divided by 4. To simplify it, we're going to cancel out this radius squared. This radius to the 4th is going to turn into a radius squared, and that's going to leave us with depression is equal to the angular frequency squared times the radius squared times 4 times the gravitational acceleration, or divided by 4 times the gravitational acceleration. So now that we have the depression fluid volume, we need to figure out at what point the liquid is going to equal the height of the cup. And at that point, what the angular frequency is, because anything greater than that will spill the water out. So we can set that equal to the height of the cup. So we have the fluid that's in the cup that's not spinning upwards in this parabola area. So that's going to be the initial fluid height minus the depression fluid height, which is the angular frequency squared times the radius squared divided by 4 times the gravitational acceleration. And then we can add that to the height of the water that's spinning, which we defined over here. So that's going to be add this height here, which is the angular frequency squared times the radius squared divided by 2 times the gravitational acceleration. So basically what we have here is a negative 1/4 plus a 1/2, which would give us a positive 1/4. And then we can plug in those other terms, which is the angular frequency squared times the radius squared times the gravitational acceleration. And we have the initial height is equal to the height of the cup. And so now we can move around the terms so that we can isolate the angular frequency. So we can move the height of the cup, or the initial height, to the other side. So that would give us the angular frequency squared times the radius squared divided by 4 times the gravitational acceleration equals the height of the cup minus the initial fluid height. We multiply by 4 times gravitational acceleration and divide by radius squared. So it's going to give us the angular frequency squared equals the height of the cup minus the initial fluid height times the quantity of 4 times the gravitational acceleration divided by the radius squared. We can square root both sides. So that's going to give us the angular frequency equals 4 times the gravitational acceleration times the quantity of the cup height minus the initial fluid height. That's under a square root divided by the square root of the radius squared is going to just be the radius. So that is our final formula for the maximum frequency that this turntable can spin before the water in the cup spills out over top.